Hello, welcome to the first lesson in IGCSE Geography. Welcome, welcome. Now today we're going to jump in with our first unit, which is all about rivers. Oh yes, rivers and the way they interact with our environment and the way that we interact with them. So a whole lot to get through. Rivers are a very common geographical feature on Earth. You've probably seen one. You might even have been in one. But how they work is what we need to study over this first unit. Now, today we're talking the hydrological cycle. That's our title. But just to give you an overview of this unit, we're going to be starting today with the hydrological cycle, how water moves around and is stored within our planet. We're going to look at weathering and erosion. That'll be in video number 2. We're then going to look at upper course features and lower course features. That's lesson 3 and 4 respectively, and then we're going to pause to look at a case study for lesson 5. In lesson 6 we're looking at supply and demand. In 7 it's flood hydrographs, which leads us with number 8, all about how to defend against floods. Good ways, bad ways, different ways. Okay, so we start today with our hydrological cycle. It's not a bike that rides on water. That's just a funny joke. No, the hydrological cycle you've probably heard of before. Even if you haven't heard it named this thing, usually it's just called the water cycle. And if you're used to Key Stage 3 geography or Key Stage 3 science, then you should hopefully have heard of the water cycle before. What we're going to do today is use this diagram, which is slightly under my shoulder, there we go, to explain all the different things that are going on in this great big cycle. Now, the first thing we need to know, just a little note on the colours that you'll see in these lessons. Blue is my colour for keywords, so if it's in blue, it's a keyword given to us by the exam syllabus to tell us that we need to understand that word. Super important, because they will ask questions that use the keywords and they won't explain them. They won't say, explain what evaporation is, and then in brackets say, evaporation means this. They're not going to do that. You have to know what evaporation means, right? Or you won't be able to access the questions. So understanding the keywords and being able to use those keywords will be the key. That's maybe why they're called keywords. The key to doing really well in this exam. Things in green that I put here, those are example questions. You can try those in your own time. We'll talk about different varieties of green questions as we go through. Sometimes they'll just be there on the board and I'll barely pay any notice to them, but sometimes I'll talk you through how to do it. We're looking at 4-mark questions today, so yeah, we'll answer that question at the end. Things in black, purple, orange, they're just there because I like the colours, really. They don't have any special significance. But blue, keywords, green, questions. Alright, so let's start with 2 of those keywords. The first is closed system. Now, there are 2 types of systems in the universe. You either have closed ones or open ones. And there's a whole load of examples of closed systems, right? A closed system is the water cycle, or the water cycle is a closed system. A closed system has nothing entering it and nothing leaving it. In fact, the system just works in a sort of recycling motion. Now, that might not make sense at first, but let's talk about what an open system is and then compare the 2, and that might make more sense. So an open system is a system where things come into the system. They usually, either flow around, move around in that system. Often they are changed, into different things, and then they leave the system and they're gone. So there's a lot of open systems that we can think of. Probably one of the simplest to think about is our digestive system, right? We put food in, it gets processed through our bodies, and then poop comes out. So we've put a material in, we've got a product out, and in the middle it's gone through all kinds of different processes. A car engine, really similar. You put fuel in, the fuel gets burnt up and used, and it comes out as exhaust fumes and movement energy, and well, then you've got to put more petrol in again. Because human digestive systems and cars are open systems, we're constantly having to input new product, food, or petrol or whatever. A closed system then now makes more sense. A closed system is where you don't put anything in and nothing comes out. In fact, everything just rattles around within the same system. And the water cycle is a brilliant example of that. You know, we have other examples like the rock cycle and the carbon cycle, but the water cycle is probably more truly closed than either of those two. There is no extra water on this planet. Water doesn't appear, it doesn't get created, nor does it get destroyed. All water can do, or all it does do, is change form, change its temperature, change its runniness, so to speak, and its position on the planet. But there's this one certain amount of water which just keeps getting recycled. Now the vast majority of that water is in the oceans, like the vast majority, 97% in fact of all the water is sat in the oceans. So that's nice and straightforward, right? The ocean is most. But we need to know about two things that happen in this closed system that is the water cycle. The first thing that we need to understand is that there are stores. There are places shown in green on this diagram. This diagram can be found in your textbook, of course. But the green labels are places where water is stored, so stops moving for a period of time. Now, some of those are actually not long. So a river, like the topic of this unit, is a store. It's a place where water is stored before it gets to the ocean. It might not stay there for long. The water might be in the river for less than a day before it's out into the ocean, but we still call it a store. There are some stores, though, which are incredibly old, have been there for a long time, particularly the ice sheets. If you think about that ice on the top of Mount Everest or that ice in Antarctica, it's been there, some of it, for millions of years, just stored, waiting to start moving around the system again. The ocean itself is a store. We can see here that it's labelled the saltwater store, but really, dude, it's the ocean. Okay, it's got a simple name. So we'll go through those stores, but we're also going to go through the flows, and the flows is where things get interesting. The flows are where water changes its position and often changes its state. You know, there are three states that water can be in. It can either be solid, and we call it ice. It can be liquid, and we just call it water, or it can be gas, and we call it water vapor or steam or something like that. So these three states are constantly sort of individual water droplets are moving through those three states as part of the water cycle, sometimes fast, sometimes incredibly slow. But a flow or a transfer, and either word is fine, these are telling us how water is moving. Again though, even though a river is moving water, it's not a flow. Even though we say, look, that river is flowing, in the hydrological cycle, it does not count as a flow because, well, it's like a place where the water is for a while. Okay, so let's start with the three big flows, and we'll talk more about the stores as we get to them. But our three main flows, how do I fit that on there without me being in the way? Let's move it over here for a second. Okay. No, there's no way of getting it all on. Okay, let's start with evaporation. Evaporation is probably, hopefully a word that you've heard of before. Evaporation is simply the word that we use for when water changes state from a liquid into a gas. This happens because of solar energy, so heat energy from the sun, and it happens everywhere. The surface of the ocean is constantly changing into a gas and floating up into the atmosphere. It happens in our rivers, it happens when water falls onto leaves, it happens all over the place, and it's very important, especially when it comes to our open ocean, our saltwater store, because all the water in the ocean is very salty, not good for us to drink. We would die if we drank that. But evaporation means that the water content is taken out of the ocean, leaving the salt behind. You don't get salty rain or salty clouds. That's because the salt does not evaporate and the water does. So we have evaporation going up to the atmosphere. This is happening because of temperature rise, heat. but the atmosphere is very cold the further we go up. So as that water goes higher up into the atmosphere, as a gas, as water vapor, it starts to cool down. And as it cools down, it moves from the state of vapor, gas, back to liquid again. And we call this process condensation up here. And the most obvious sign of condensation is clouds in the sky. Those clouds are vapor that has been converted back into a liquid but is suspended in the air. Tiny particles. A cloud is basically a framework of dust. Those tiny particles of dust, each one has a water droplet around it, and they club together to make these clouds until eventually the clouds will burst and we get precipitation. Precipitation is usually rain, but really it's a fancy word for any kind of water that's falling back to Earth. So it could be snow, right? It could be that the clouds are so cold they're actually made of solid ice crystals and we get snow instead. So that's evaporation, condensation, precipitation. Precipitation, remember, usually rain, but it could be sleet, hail, snow, whatever. So those are our three main flows. And if you've done this at Key Stage 3, hopefully that makes sense. You're familiar with those. But we also have some flows under the ground. So let's go back into our diagram here, this part of the diagram now. So we can see here a few words. We've got infiltration, percolation, groundwater flow, and one that I've had to write and put on myself called through flow. Not sure why it's not on the diagram. Maybe it's an oversight by the textbook. Now these four words, through flow, groundwater flow, percolation, infiltration, these are all talking about how water enters into and then moves along underground. So infiltration is where water, and we can see the arrows here giving us this impression, it's where the water filters down into the soil. So if you're a bit of water and you're moving through the soil, we call that infiltration. Now below the layer of soil on our planet, there is of course a layer of rock. And if water starts to go through that, so it's already been through the soil and now it's going through rock, we call that percolation. So infiltration, going through soil, percolation, going through rock. But then when it starts to move downhill, as all water will, it's very lazy and it always follows the laws of gravity, it will move through the soil and it will move through the rock. And this is where those other two words come in. So water moving through soil, downhill, along, like through the soil, not into the soil, that's infiltration, but along through the soil. And that's called through flow. And the same thing with rock, when the water is moving through the rock, that's called groundwater flow. So we can say things like, well, the water infiltrated the soil and through flowed. We can say the water percolated into the rock and joined the groundwater flow, something like that. So really it's just, is it soil, is it rock? They have different words to go with. We've also got a couple more here. Got to get used to this zoomy thing. Here we have evapotranspiration, which is very much like evaporation, but we are helping living things like humans and plants. We tend to expel water when we breathe. There is water within us and it comes out as vapor. You can see this best on a cold winter's day when you go outside and you breathe and you look like a dragon when all that white stuff comes out of your mouth. That's because the water inside us that we're constantly breathing and spitting out, tiny particles, it's not that disgusting. Normally you can't see them because they're the same temperature or roughly the same temperature as the air around them. But when the air is very, very cold, it will go straight through that condensation process. So your air, the warm water comes out of your mouth, it condenses in the cold winter air, and then we can see it as a white visible cloud. We also have runoff. Runoff is, well, it kind of does what it says on the tin. Runoff is where water rolls downhill. Yeah, you put it on something, it runs off. Yeah, so it always follows gravity. Think of water off a duck's back. That runs off because the feathers of a duck are so nice and waterproof. But it works on any surface really. Some surfaces run off faster than others, depending on how steep the surface is or what material it's made of. But runoff is just the word that we call water when it's running over the ground. So it hasn't infiltrated, it hasn't percolated, it's on the surface of the earth. and it's just rolling down. Yeah. If you have ever been in a big rainstorm, you'll see runoff, like visibly, as it, water creates little runnels on the street or whatever. So those are our major transfers or flows. Now, knowing these words is really important. They might say in the exam, they might give you a question saying, name one transfer in the hydrological cycle. I mean, if they do that, and you mention a store, if you say, oh, well, one transfer is a glacier, then that's a wrong mark, right? You haven't got the mark. So knowing the difference between a store and a transfer and all the words that fit is really important. Let's go look at those stores, shall we? So we've got the biggest one. We've got the saltwater store, the ocean, just above my head here. We've then got the surface store, which is lakes, rivers, that kind of thing. We've got a fancy word up here, though, interception. If you can see that just under there, under precipitation. Interception is when leaves, roots, bark, parts of usually trees, but it could be anything. It could be an umbrella. It could be the roof of a house. But interception is where something stops the water momentarily. It holds it, right? So if I poured water straight onto a desert, the Sahara, it would just sink down into the soil. It would infiltrate into the sand. But if I drop that same water onto a forest, actually it probably wouldn't infiltrate a lot of that water. It would land on leaves and branches. It would get caught up in birds' nests and things, and it would just sit there. That's interception, right? So it's a store, but it's not a very long-term store. That water that gets trapped on the leaves on a tree on the rainforest, it might well evaporate a couple of hours later, but for now, it's a store. We've also got here, if I move that way, our cold stores, which we've mentioned before. So ice sheets, called the surface store here as well, but ice sheet is the important bit, and glaciers, which are frozen rivers. They move very, very slowly, but they do move. But if a river is a store, then a glacier certainly is, because the water stays in a glacier for far, far longer. We can also see underground we've got a store, the store aquifer. Eventually, once water has infiltrated and percolated, it will get to something called bedrock, which is almost impossible for water to pass through, and it will just sit there under the ground, sometimes in great big sort of underground lakes and rivers, sometimes just loads and loads of water droplets caught up in tiny cracks in rock. But we call this an aquifer. It seems like they've spelt it wrong here. The textbook has called it an aquifer. It's not an aquifer. It's an aquifer. Ignore that naughty I. I'm going to put my mouse over it. Bad eye. So, aquifers are the general name that we give any water that's stored underground. Okay. So hopefully, I know that's a lot there, but hopefully that makes a bit of sense. It would be a very good idea to make your own copy of this diagram to show the different flows and stores so that you can really get a grasp on which is which. The color coding here helps a lot. And here's a 4-mark question down the bottom. Explain 2 ways water is transferred in the hydrological cycle. That's the kind of language that the exam will use. So to do that, you would have to give 2 different transfers and explain each one. Usually in the exam they give you 3 or 4 lines for each point that you're making. So you might pick a transfer at random. I don't know. Let's go for precipitation, right? So we would say precipitation is a way the water is transferred, and it works as water droplets have formed and become heavy in the sky, and they fall down to earth as usually rain. Excuse me, my voice. Usually rain, or sometimes snow or hail. Yeah, that would be a good explanation of precipitation. We might then say, oh, evaporation is another transfer. And evaporation happens when heat from the sun warms water and makes the particles very, very fast, and they become a gas. Yeah, something like that. You get 4 marks. So it's picking 2 separate things and explaining each, not in crazy detail. You don't need to write a small essay on, exactly how evaporation works or whatever, but being able just in a couple of sentences to say, yep, this is what evaporation is, or groundwater flow, or whatever. That will get you the marks you need. All right, let's move on to the next bit. Here we have a river basin. Oh yeah. Now, a river basin is a geographical area. It's an area around a river, right? And it's the area around the river where everything drains into that river. Sometimes it's best to think of rivers as just these great big drainage gap sort of trenches that take water from the landscape and dump it out at sea. That is essentially the function of a river, right? It takes water, collects it, transfers it into the ocean, even though it is a store. Awkward, isn't it? Now, a river basin then is a geographical area where every drop of water that falls into that area will end up in that particular river. Now, rivers are more complicated than just a straight line, as we can kind of see on this rather busy diagram from the textbook here. Rivers are actually made up, or river systems are actually made up sometimes of hundreds or thousands of little rivers that run into each other, and then they end up as one great big flow, right? So here we can see there's lots of these little rivers, we call these tributaries, that are entering into, eventually, its own sort of standard massive river. Now, if we were to take some water and pour it, let me get my pen here, well, let's say we're going to pour it just here. Now, that's outside of the watershed, which is this blue line. That means that any drop of water that falls where I've put that little black cross is going to flow probably the other way down the hill or into another river somewhere else that isn't on this diagram. But if I put a little cross here, ooh, I can't draw crosses very well. If I put a little cross there, well, that's within the watershed. So that means that any drop of water that falls right there is going to end up, by hook or by crook, in this river system. We'll talk about ways in which water enters river systems in a future lesson, but you know, as a general point, that stands. So the watershed is the boundary of a river basin. If water falls within that boundary, then it will eventually, unless it's evaporated or like carried off, you know, by a creature or something, it will end up naturally just flowing into that river. Could take ages, could take a while, percolating through the soil, infiltrating through the soil, percolating through the rock, and it could take centuries for it to filter through that rock and enter the river system, but it will do eventually. Anything outside the watershed will flow somewhere else, either directly into the ocean. So if there was like one here, we wouldn't say that was in a watershed because it's just going to roll straight into the ocean. It doesn't need a river. But these ones just on the outside here, well, they're going to end up, you know, filtering through, and because of gravity, you know, usually the watershed is around the highland, right? So you've got high hills or mountains all the way around the river, and everything sort of drains that way. But if you put that water outside the drainage, the river basin outside the watershed, then it will not end up in that river, but in a different river system instead. Now, this diagram is a bit busy, and a lot of the words we've covered already, so hopefully they're familiar to you. But you can see here they're showing those main flows out of the river. Now, interestingly, we talked about the water cycle as this open system, closed system. Nothing comes in, nothing comes out. It's just a closed system where everything just, you know, moves around. There's the same amount of water on the planet, almost, as today as there were, I don't know, 3 billion years ago or whatever. But a river itself is actually an open system because water enters, you know, it filters into the river by hook or by crook, and it exits into the ocean. So the river itself is an open system, even though it is part of a much larger planet-wide closed system. There we are. So you can have both kind of systems functioning on the same kind of level. Some questions to have a go at here, which we'll talk about in relation to this, but explain 2 ways water is transferred in the hydrological cycle. That's the question we had earlier. And then explain 1 way water... oh no, I'm writing instead of moving. That's no good. Explain 1 reason why water runs off urban areas faster than wooded areas. All right, that's a 3-mark question. We deal with that quite differently. But let's have a look at this diagram, and then we'll see if we can answer that question. So, this here looks like a crazy golf course, but it's not. It's another diagram from the textbook, which is showing us how water interacts with different kinds of surfaces. So the water falls as precipitation. Yeah, it comes down from on high, down from the sky. It lands on a whole range of different surfaces. Now, up here at the top of this mountain, the runoff, the speed that the water runs down the mountain is going to be quite high because it's very steep. Gravity is doing its thing. If you drop water on a flat surface, it's not really going to move much, but if you tilt that, it's going to go down. So the steeper the mountain, the more rapid that runoff is going to be. But we've got two types of material on this mountaintop. We've got rocky bits and we've got grassy bits. Now, if it falls on the grass, it's going to roll much slower because it's going to be intercepted by that grass. It might even infiltrate down into the soil and then start moving slowly. But if it rolls onto these rocks here, well, it's going to roll off real fast. These are impermeable rocks, which means they don't let water through, which means the water has no choice but to run straight off. And especially at that rate, at that gradient, it's going to run off pretty quick. Now, further down the mountain, we've got these little holes representing water that is infiltrating and then percolating down into the mountain itself, into this weird little cave system here, which looks quite beautiful. That might well slow it down, but here we seem to have some underground rivers, or some rivers which are going underground are going to pop out further down. And in those rivers, the water is going to probably flow quite quickly and unimpeded. But then we get to the interesting bit. Let me zoom in here. Just to explain what's going on here, we've got the ocean is our bottom strip. We've got two mighty rivers coming down here that have come out from the hillside. And then we've got this green bit that represents a big forest, and we've got this greyish bit which represents a massive city. Now, the water moving through the forest is going to be quite different than the water moving through the city. And that's because of the type of surfaces, the kind of geography that we've got. In the forest, there's going to be a lot of interception. As rain falls around here, it's going to get caught on those trees and roots. It's not going to filter very quickly into that river, which means that this river is probably going to be far more gentle than the river moving through the city. And yes, I know that both rivers eventually move through the city. But in the city, we're going to have much faster accumulation of water. Because think about what cities are made of, and towns and villages. We cover the roads, the floor with tarmac and concrete. We build buildings with roofs made of tiles or glass or plastics. All of those things are impermeable. I can't say the word impermeable without bubble. Anyway, you'll get used to that. Impermeable surfaces that water can just run straight off. There's very little interception in a city. Even, the roads don't intercept water. They just let it run off, which means that any rain that's falling in this city is probably going to enter that river very, very quickly, compared to the forest where the rain that falls is caught by the leaves, intercepted, and enters the river slowly. And why is this a problem? Well, the faster water enters into a river, the more likely there is of that river not being able to cope with the amount of water and flooding. And flooding can sometimes be a right old problem, but we'll talk about that another time. So let's try this 3-mark question, and let's just compare it against a 4-mark question. This question here: explain one reason why water runs off urban areas faster than wooded areas. Now that sounds much easier than explain 2 ways water is transferred in the hydrological cycle. We've got to only talk about one thing here, and we've got to talk about 2 there. At first glance, the one is going to be easier, right? But it's not. It's a trick. It's a lie. A terrible lie. A 3-mark question in geography is actually a little bit more difficult than a 4-marker, in my opinion, because of the level of detail. For a 4-mark question, we're getting 2 marks for each explanation we give. So we're saying, this is a transfer, this is what it means, boom, 2 marks. We can't do that with a 3-mark question. If we're going to get 3-mark questions, we're going to have to answer in a lot more detail, because we're going to have to get 3 marks for making 1 point, rather than 2 points for making 1 point, 2 marks for 1 point in a 4-mark question. So when we're trying to do our 3-mark questions, the trick is to clearly state what's going on. So in this case, we would pick a point. We would say, oh, well, water runs off urban areas faster than wooded areas because cities are full of impermeable materials. Nice. We'd get a mark for that. That's a true fact, that. But then we've got to explain it, and we haven't just got to explain it in brief like we do for a 4-mark question. We've got to explain it in some detail in order to get both of those extra marks. So we might give examples. That would help us. We could say, well, the city is covered in glass and concrete and water runs straight off this really fast. But then we could compare it to the woods, right? We could say, well, in the woods there's lots of plants and they're going to intercept water a lot. Therefore, runoff is going to be slower in the woodland and faster in the city. And it's that level of detail that we would need to get the 3 marks. So never look at those 3 marks and go, oh, well, that's simple. Simpler than 4 marks. No, it's not. It's more complicated because you have to explain one thing in much more detail than you do 2 things in simple detail for a 4-mark question. Hopefully that made sense. I'm not sure how well I explained that. Let me pause just for a second. Okay, that worked. So that brings us to the end of the first lesson, and already I'm sure your head is spinning with a lot of different words and concepts, right? It's okay. Some of these we're going to go into deeper, so things like factors affecting runoff and some of these different stores and transfers we'll look at in more detail as we go through, but hopefully you've got a big list of different sort of key words inside your head now, and you've got an idea that water is moving around the planet constantly in this hydrological cycle, and the way that that water interacts with the solid world around us is quite significant. And all of this leads us, of course, to next week's lesson, which is going to tell us, or lesson number 2, which is going to tell us how these different processes really get going. Alright, so I look forward to seeing you then. Bye!